So one thing that we want to consider is the special case where we have motion only in one direction. We've been talking about displacement as a vector, and considering the more general case, like with the boat example, where the motion was in more than one direction. But if the motion is in only one direction, the case becomes a bit simpler. In that case, we can describe the motion by first picking an origin, and then describing the motion as being in the one direction with respect to that origin. So if we look at this car example, the origin that we've chosen is this speed limit sign. That's where we put the 0 of our coordinate system. And then x is used to describe how far the car is in either the forward or backward direction from that speed limit sign. We've defined the forward direction as being the positive x direction and the backward direction as being the negative x direction. So if we look at the motion of this car, it starts out 30 meters from the speed limit sign in the positive x direction. It moves forward to this position which is just shy of 60 meters in the positive x direction, and then the car goes into reverse. So it starts backing up. At location D, it's at the origin, and then in locations E and F, the car is in the negative x direction. So we can make a graph of this motion. So we start out here at 30 meters in the positive x direction away from the origin. The car moves forward, and then it starts going into reverse. So it moves at location D to the origin, and then has negative location values. And so this is just an example of how if you have simpler motion, where it's all in one direction, you can pick an origin and then use positive and negative values to say what side of that origin your object is on. So next we want to look at velocity. And velocity is defined as being a change in displacement with time. So if we look at this picture of the basketball going into the hoop, we can see the path of the ball. So this would be the path length, and then the straight distance from its beginning to its ending point is the displacement. And the velocity is this displacement divided by the amount of time it took to undergo that displacement. So we would define the average velocity as being the displacement divided by the time. Now velocity is a vector, which means it is comprised of two parts. You have the speed of the object, and then also its direction. So velocity tells you not only how fast the object is moving, but also the direction in which it is moving. And so that means we can change either the speed or the direction to have a change in the velocity. So if you have an object and it speeds up, or it slows down, or it changes the direction it's going, those all represent changes in the velocity. So if none of those things are happening, if the object is moving with a constant velocity, and it's also not changing its direction, so it's only moving in a straight line in one dimension, then we can describe that motion more simply. We can find the change in the position, the displacement, is just the change in the position in one direction, or the final position minus the initial position. Then the velocity would be the change in position with time, and here we've gotten lazy and just use x instead of x sub f as the final position. X sub 0 is the initial position. And sometimes we get lazier still, and instead of a time interval written this way, we just write time, and this would be the final time. We're assuming that we started recording time at t equals 0. So if this is the case, if we have an object which is moving in just one direction, and it's moving with a constant speed, constant velocity, then we can write down this equation for determining position. So what this expression is saying is that the final position of an object, its final x coordinate, will be equal to its initial position plus the velocity times the amount of time it was undergoing that velocity. So let's take a look at using this equation to solve a problem. So in this problem we have two trains. Train A starts from small town and heads east. At the same time, train B starts from Bigville and heads west. Assuming train A travels at 30 miles per hour and train B travels at 40 miles per hour, and the towns are 100 miles apart, how far away from small town are the trains when they meet each other? Okay, so to do this problem, and anytime you're doing a problem like this, it's a really good idea to start out with drawing a picture that we can label with some of the facts that were given in the problem. So let's do that. So if we are going to make a picture of this, we have two towns that we're starting out with. We have small town and we have Bigville that are located a certain distance apart from each other. So those are my two towns. And one thing I should really do, and do whenever I'm doing a problem like this, is to figure out my coordinate system. So in this case, all of the motion is in just one direction, which I can call x, but I have to figure out where the origin is, where my x is equal to 0. So I'll choose small town as being the origin of my coordinate system. This will be convenient because the problem asks how far away from small town do the two trains meet. So if I choose small town as my origin, then the x coordinate will give me the distance from small town. So I'll choose this as my origin, which means this is where x is equal to 0. And since Bigville is 100 miles away, this is where x is equal to 100. Now, I know that train A starts out at small town. So there's train A. It starts at small town and it heads towards Bigville. And train B starts out at Bigville and it heads towards small town. And at some point, the two trains are going to meet up with each other. So since both of these trains are traveling with a constant velocity, they're traveling with a constant speed and they're not changing direction, I can use that expression that we found on the previous slide. That is that the final position of an object is equal to its initial position plus its velocity times time. So let's first write down this position, incorporating the facts that we know in regards to train A. So for train A, I'll write down that the final position of train A, here x sub A means train A, that's going to be equal to the initial position of train A. Well, where did train A start out? It started out at Smallville, and the initial position of Smallville is at x is equal to 0. So my x naught for train A would be 0 plus this velocity of train A. Train A is traveling with a velocity of 30 miles per hour. 30 miles per hour. And train A is traveling in the positive x direction. So I would write down positive 30 miles per hour times the amount of time that it travels before it meets train B. On the other hand, train B's final position is going to be equal to its initial position. Well, what's the initial position of train B? Train B is starting out at Bigville, which is at x is equal to 100 miles. So the initial position of train B is 100 miles plus its velocity. What's the velocity of train B? Train B is traveling at 40 miles per hour, but it's traveling in the negative x direction. So its velocity is going to be negative. Negative 40 miles per hour times t, the amount of time that it travels. Okay, so now that I can see that I have an expression that gives me the position of train A and the position of train B at some later time. So I need to know how far away from small town do the two trains meet. Two trains meet. What does that mean? Well, if the two trains are meeting, that means their positions are the same. So when they meet, that means that the position of train A is equal to the position of train B. They have the same x location. Well, I have an expression for the position of train A that I can set equal to the expression for the position of train B. So I can say that 30 miles per hour times t is equal to 100 miles minus 40 miles per hour times t. So now I have an expression that I can solve for t. T is the one variable, the one unknown in this problem. So if I want to solve for t, I need to get all my t's on one side of the equation. So I could add 40 miles per hour t to both sides, plus 40 miles per hour t to this side of the equation, plus 40 miles per hour t to the other side of the equation. So on the left-hand side, I would end up with 70 miles per hour times t. So 30t plus 40t would give me 70t. And that's going to be equal to, well, this cancels, so it will be equal to 100 miles. And then the final step would be to divide both sides of the equation by 70 miles per hour. And that's going to give me a t equal to 1.43 hours. Okay, so now I know when the trains met. They met 1.43 hours after they departed from their respective stations. But that's not exactly what the problem was asking. What the problem was asking was, where were the trains located? How far away are they from Smallville? Well, now that I know the time, I actually have a couple of different ways that I can find the location. I can take this 1.43 hours and plug it in to either my expression for A or my expression for the location of train B, because they're going to be at the same place at that 1.43 hours later. The first expression looks a little bit easier to solve, so I'll do that. I'll say that, well, train A was located at 0 plus 30 miles per hour times time, where my time is 1.43 hours, and that will give me a location of 42.9 miles. And since I defined my x location to be the distance from Smallville, train A and also train B, 1.43 hours after departing, are going to be 42.9 miles away from Smalltown. So that would be the answer to my problem. So let's look at this question. If the average velocity of an object is 0 in some time interval, what must be true about the displacement of the object during that time interval?